Hi guys, let's talk about the Hall effect. This was something that we didn't get a chance to talk about in our synchronous session, so I thought I would post a little video about it. So far we've been talking about the Lorentz force in the context of electrons that are basically in a vacuum. Thinking about lab, where we have that the apparatus with kind of the bulb, and we shoot a beam of electrons and we can deflect them with electric and magnetic fields. But this also comes into play uh, inside of a material. So imagine in a circuit, say, a slab of or a strip of metal. Suppose you have this, hooked to a battery or something. So you have um, current that's flowing through here, through this strip, and the strip has some width d, and so we have electrons would have some drift velocity inside the strip for thinking about the microscopic picture. And what we would notice, and suppose this whole thing here is a magnetic field that's pointing into the page. So what we would notice is those electrons would feel a magnetic force pointing down. Actually, let me put that in a different color here. Like this. Do your right-hand rule. And that force, be of course Q V cross B. Since they're perpendicular, this just looks like, negative the charge of an electron VB. Now, what would happen is there would be charge that would kind of accumulate along the edge, or that's one way to think about it. And so this would look like an electric field. And there would be a force that would be due to that as well. Remember, that's just Q times the electric field. And we're going to call that electric field the Hall field after the effect. So this would be, the electron times that electric field. And what's going to happen is that's going to reach an equilibrium. And so this magnetic force and the electric force are going to be equal. And so we can set these two things equal to each other. Notice the electron will drop out. And we have this relationship between the electric field, the Hall field, and the drift velocity. Sorry, let me be more careful here. And the magnetic field. Now, normally what we would do is we would express this electric field as the voltage, which is called the Hall EMF, over the plate, the width of the strip. So in other words, we'd have this relationship. And this is because you can measure, the potential. So let me actually be a little more clear here. We'll call this EH, and then the potential difference across the two sides of this would be the Hall EMF. And this is the relationship that we usually talk about when we're talking about the Hall effect. And so you could use this for different things. You could measure if you know the width of the strip and you know the drift velocity, you could measure the Hall EMF and find B. You could, do other things. You could solve for the drift velocity. You could solve for, whatever you want. And this is one of the common uses is you can use this as a magnetic field sensor. And it's pretty common to do that. So, or you could, you could measure other things. You could, if you knew the magnetic field and you knew the Hall voltage, you could find the drift velocity or something. So let's look at one example. This will give us a chance to connect back to drift velocity as well, which is sort of a good exercise in dimensional analysis and whatnot. So let me paste an example in here. Let me make this a little bigger. So we use a probe that uses the Hall effect to measure magnetic fields. A 12 amp current passes through a 1.5 centimeter wide, 1.3 millimeter thick strip of sodium. So let me try and draw this. If the Hall EMF is 1.86 microvolts, what is the magnitude of the magnetic field? Assume the magnetic field is perpendicular to the flat face of the strip, and assume one free electron per sodium atom, and that the specific gravity of sodium is 0.971. So we have this current of 12 amps. We're going to assume that this, the EMF across here is 1.86 microvolts. This has a thickness of 1.3 millimeters, and the width of the strip is 1.5 centimeters. And what else? The magnetic field is perpendicular to the face of the strip. So as I have it drawn here, we could imagine it's going like this through the strip. However we want to draw this exactly. Coming, you get my drift here. Okay, so it's, if this was flat, we would just draw like, something like this. In any case, so we know the Hall voltage, we know the current. What we want to find is the magnetic field. So what is B is what we're after, magnitude. So let's take a look. Our relationship that we just derived was that the Hall EMF looks like the drift velocity times B times the thickness of the width of the strip. And we're going to solve this for B. And we know the width, we know the EMF. The thing that we need is the drift velocity. So what is drift velocity again? So we can look back to section 25.8. And we can relate the drift velocity to the current density. So remember, J, the current density, is the current per cross-sectional area. So you can kind of imagine, this area of our strip is the cross-sectional area. And this is related to the number density, the charge of the electron, and the drift velocity. So we could come up with the current density. We know the charge of the electron. the missing ingredient is the number density. So how many charges per volume? The number of electrons per volume. Now we're told that the specific gravity, what the specific gravity is, and the specific gravity, what is that again? That is mass per volume, but we want number per volume. So what we can do is if we multiply the mass per volume times the moles per mass times the number of atoms per mole, and we know that there's implicitly here, there's one carrier, one electron per atom, then this should give us, well, let me see here, the specific gravity. So this is the specific gravity, sorry. This will give us something that would have units of number of electrons per volume. So let's do that. So this will be 0.97 grams per cc times the molar mass of sodium is 23 grams per mole. There are 6.022 times 10 to the 23rd particle, or per mole. And so you can see this will give us something that will have units of number per cc. So we would also want to multiply this by a factor of 100 cubed, because there are 100 cubed cc's per meters cubed. So this will put it in proper units of meters. So when we multiply that stuff out, we find that the number density is 2.54 times 10 to the 28, charges, free electrons, whatever we want to call it, per meter cubed. So we have n. If we have n, we can get the drift velocity. We can basically solve this thing here. The drift velocity will be I over A cross section 1 over n e. Doesn't really matter the sign of that. So if we put those ingredients together, let's do that over here. How about, I'll do it right here. That'll be 12 amps divided by, the cross-sectional area is going to be 0.015 meters times 0.0013 times our 2.54 times 10 to the 28th. Actually, let me move this stuff. Put it over here. So this is our, number density times the charge of the electron, coulombs. Put those pieces together, we find that the drift velocity is 1.5 times 10 to the minus 4 meters per second. Now we're ready, since we have the drift velocity, we can put it in to here to find the magnetic field magnitude. 1.86 times 10 to the minus 6 volts over this 1.5 times 10 to the minus 4, and the width 0.015. And this will give us something 0.8 Tesla. We can check our units here. So these units are maybe a little bit unfamiliar. We have volts per drift velocity, so that was in meters per second, times a factor of meters, the width. So what's a volt? That's a joule per coulomb, and a joule is a Newton meter. So this is a Newton meter per coulomb divided by meters squared per second. So we're left with a Newton per coulomb meter per second. Coulomb per second is an amp, so this is a Newton per amp meter, and that's our Tesla. So the units check out. Hopefully this example gives you some stuff that will be helpful as you work through stuff about the Hall effect. You can see back to section 25.8 for help on the drift velocity and what that's about. And yeah, so this, this is a pretty widely used magnetic sensor kind of technology, so it's good to have this, have seen this.